This is Nanoscape. I'm Seth Zimmerman.
And I'm Erin Spain.
On this show, we venture into the frontier of nanotechnology
with experts in the field who are turning the science of small into the next industrial revolution.
This podcast is brought to you by the International Institute for Nanotechnology at Northwestern University. Nothing breaks all at once. When a plastic component cracks or a textile fiber frays, the damage doesn't start where you can see it. It starts much earlier, at the nanoscale, in the way molecules move, stretch, and slide past each other.
Today, we are talking with Northwestern University Professor Cécile Chazot about understanding polymers, the materials that make up everything from clothing and plastics to advanced textiles. Her lab studies how these long molecular chains behave at the nanoscale and how understanding that behavior can help scientists design materials that are stronger, more durable, and more sustainable.
Cécile is the Julia Weertman Professor of Materials Science and Engineering in the McCormick School of Engineering, where she leads the Sustainable Polymer Innovation, or SPIN, lab. Her group focuses on creating sustainable textiles with new chemical properties. And we're thrilled to have her on the show to talk about how polymer structure shapes the properties of materials and how we can redesign those materials to perform better and last longer. Cécile, welcome to the show.
Thanks for having me.
Let's start big picture. When we talk about polymers, plastics, fibers, textiles failing, what's the first step of this failure? Where did it begin?
Where does it start? It depends on how the molecules are arranged, actually. And I think you can get a sense about how different that is by just considering natural fibers, things like your hair, things like wool, things like cotton, and more synthetic fibers that you see more in activewear, like polyester or things that are like fully man-made. Where it starts, regardless of the way it's arranged, it's usually those molecules sliding past each other. But sometimes it's not. Like wool and your hair, for instance, you have a large diameter fiber, and inside there's a bunch of nanofibers, which are called intermediate filament, and they're surrounded together by goop, which is a bunch of smaller molecules. And when your hair split, for instance, those are those intermediate filaments that are being separated without necessarily having molecules that are at the smaller scale sliding past each other. But if you think about a synthetic fiber, for instance, like polyester, it doesn't have what we call this hierarchical arrangement. It's not a fiber made of smaller fibers, made of smaller fibers, made of macromolecules. It's just macromolecules all aligned with each other, and they just slide past each other. That's the beauty of fibers and polymers, and the beauty of the difference between the typical synthetic polymer and a typical natural polymer, where natural polymers tend to have this hierarchical order where macromolecules, they twist together, they make a smaller fiber. Those fibers, they twist together, they make a slightly bigger fiber. Then all those fibers, they pack together and they make your hair.
So for people who do not live in polymer land, what are the big levers that decide whether a material bends, stretches, snaps?
So many things. So a polymer, it's called a macromolecule. Macro because it's big, a molecule because it's a molecule, but it's not like just a couple carbon bonds. It's thousands and thousands of carbon bonds. And when I teach introductory polymers, I said to my students, a molecule is basically a bead, and your polymer is you took all those beads and you made a necklace, and they're joined together by carbon bonds. So what makes things slide past each other, break, and all that stuff is going to depend on how big are the beads, how stiff is the necklace, and how long is the necklace. Or if you have a bunch of necklaces, are two necklaces tangled together and held together that as you pull on it, it's actually catching on something? Or do you have just a bunch of necklaces that are like very nicely aligned with each other, and when you pull on them, they just slide past each other? So what we do as polymer chemists is we try and think, I'm going to change this bead. Or you say, I'm going to make my necklace longer. Making my necklace longer is what we call in polymer land molecular weight, which basically tells you how many repeat units you have, how many of those beads you have in the necklace. Or you can say, instead of using spherical beads, I'm going to use those long rectangular beads. That's going to make my necklace stiffer, and it's going to be much harder to actually have it tangle with something else, but they're going to slide past each other much easily. Everything you can conceptualize in this idea of like, I got this box full of necklaces, what happens when I grab a bead and pull on it? That's basically what happens at the nanoscale as you pull on a polymeric material.
So you learned to sew as a child growing up in France and spent years working with fabrics directly. How did that early hands-on experience influence the way you think about designing polymers in your lab today?
It's not like, oh, I always thought that my crafting experience and passion was going to be part of my research. I think that's something that came relatively late. Kind of a big aha moment is I did crafting that got me into wanting to do engineering. I wanted to be an aerospace engineer. I did a lot of work with structural composites. I also did work in colors and color science based on polymeric materials. And I was trying to figure out what did I want my lab to do. When I start my career, what is going to get me excited every day to go to work and teach those students why this is so important to work on polymer science. And it came about because a lot of people looking at fiber science just because of the interaction with other faculty and conferences. And I saw that a lot of people in academia were like, oh, I'm making a fiber. That means I'm doing textile research. And they make a fiber and they say, we could make textile out of this. And I was like, not really. If I buy polyester fabric, the weave is going to matter. If it's a jacquard weave, the fabric is going to hem differently and it's not going to look the same. I'm not going to use polyester crepe to make a couch, but I'm also not going to use polyester twill to make a wedding dress. Texture matters, the hand matters, the feel matters, the drape matters. And that kind of got me thinking that it's crazy that all the polymer we use and love were basically invented in a 30-year span between 1930, which is Carothers discovering nylon, the 1960s and 70s, which is the invention of elastane, which is what makes all your clothes stretchy and all that stuff. We didn't even know as a scientific community what a polymer chain was until the macromolecular assumption in the 1920s. And now we have all those sustainability issues with those fibers because that wasn't a design constraint. Can I, in my 30-year career, try and reconsider the constraints we're working within and develop new polymers that actually are more sustainability focused while having the same performance as all the synthetic fibers that we love and don't really know what to do with at the end of life as of now? Everyone needs clothes. You have textiles everywhere. That once you have something that works, you're like, I'm rolling with it. I'm just going.
Tell us about your lab, which you call the Spin, and you've described it as a mission-driven space built on fundamental research. How did that come to be?
So if you're like, I'm going to function exactly with the current loom, with the current fiber manufacturing process, with all that stuff, and I'm just going to mix different polymers, make new necklaces, change beads one at a time until something works. Actually, this trial and error approach is perhaps not the most efficient and best way to reach an optimal solution. That's why I call it mission-driven fundamental research. I want us to think about how is it going to be woven together? How is it going to be made? How is it going to be manufactured at scale? Can it be retrofitted in the current fiber spinning line that's done industrially speaking? But I also want us to answer the fundamental questions on the way. If I change this bead this way, how is that going to affect the fiber feel? Is it going to be shinier? Or is it going to actually be scratchy or all that stuff? And it's this idea of developing the design rules through fundamental science, through discovery, while understanding that we're not just doing it because it's cool. We're doing it because we have a goal at the end, which is to make fibers from naturally derived polymers better than synthetic fibers while being compostable, recyclable, and have a better end-of-life management.
This idea of sustainability, it often gets framed as a performance trade-off. Tell me about that. How challenging is it to design materials that are both durable and environmentally responsible?
The performance trade-off, it's not that it's not real, is that you have to understand that in our case, we work with biomass-derived polymers, polymers that are made by nature. So we don't grab the individual beads necessarily and assemble them together. We grab the necklace and we say, oh, I'm going to change that one bead, and I'm going to change that one bead. Nature has made the necklace. Bacteria, organism, plants have made the polymer chain. And this is how we used to do textiles. We didn't have synthetic fibers until the 1930s. You used cotton, which is a polymer that is from plants, or you used viscose, which was you took cotton and you reprocess it to make it a shiny fiber. You use silk or wool. All of those are polymers that are made by natural system. The reason why people think about this performance trade-off is they understand you still have this awareness that chemists in the 30s started building necklaces from scratch because they wanted to get better performance than what they had in natural fibers, which they achieved. They had stronger fibers. They had fibers that could elongate more. You wouldn't make a pair of leggings out of cotton, would you? You'd be like, first, really hot. Second, no stretch. And they achieved that. Now, the question I'm asking is, instead of starting from the beads and rebuilding the necklaces, can I take a necklace that was made by nature and change it a bit so I can actually get to similar, if not better performance than the synthetic polymer? Now, this performance trade-off is a historical way to look at it. If you're like, I want to do as well, if not better, you need to think about what is it that a natural polymer does better than a necklace you built from scratch, beads by beads. Turns out what natural polymers do better than man-made polymer is this idea of hierarchical self-assembly, which is what I started talking about. The chains naturally don't just stay as necklaces. The necklaces form helices together, and then those helices form larger filaments that are about 100 nanometer in diameter together. And then those filaments are somehow aligned in your hair, which is a bigger filament. And that's something that when we build polymer from scratch, takes such a control of regularity in the structure that we can't do very well. So I think the performance trade-off exists because instead of taking what nature did and understanding what it does best and harnessing this, we said, nature does it this way. I'm going to build a molecule from scratch that does it the way I want. And that's like, you pick your superhero, you got to train it, right? If you pick your superhero and you say, I'm going to tell Superman he has to make spider web, you pick the wrong superhero. Now, if you're trying to solve a problem where someone needs to fly, perhaps training Superman is a good idea.
We basically created these materials that cannot be recycled, and we're stuck with them in the landfills and in our oceans, right? This is a huge problem.
It is, but it's because that wasn't part of the design constraints. The design constraints were, I'm tired of those natural fibers that have no stretch and are not always super durable and not sweat wicking. And the design constraint where I want better mechanical performance. I want to pull on it and it elongates. I want to pull on it harder and it doesn't break immediately. Now it's rethinking this revolution that happens between the 1930s and the 1970s, but now being like, the design constraint is you're going to wear this garment 7 times before you throw it away. How do I make it as good as all the stuff that everyone wants, your leggings, your sweat wicking stuff, but it's not a problem if I get rid of it after 7 times?
I want to jump to something else you're working on, and that's creating color without dyes. So textile dyeing is responsible for about 20% of global industrial water pollution. And this work you're doing is creating, again, color without dyes. What's the nanoscale trick behind that, and how could it matter for water and chemicals?
Right. It's definitely a nanoscale trick. I think perhaps going back to this idea of the textile industry and things not moving really quickly, we didn't have synthetic dyes until the end of, I believe, the 1800s, so the end of the 19th century. And there was this chemist in England who accidentally discovered derivative of aniline that he could make in any color. And this is where synthetic dye became widespread into the textile industry. And a lot of those synthetic dyes, again, haven't changed a lot since then. There's other ways to make color, and one of the main way to make color is here again inspired by nature. It's called structural color. Structural because in dyes, the color you see is a chemical effect. It's a consequence of the chemical structure which absorbs certain wavelengths of light, and the light, which is the light that is reflected, is the complementary of those wavelengths that are absorbed. So your visible range of light go from 400 to 800 nanometer, 400 being violet, 450 being blue, 550 being blue-green, 600 being yellow, 610 being orange, 650 being red. So when you think about the rainbow, the blue of the rainbow is at 400, the red of the rainbow is at 650, 700 nanometers. And when something looks blue, it means the chemical substance you had in it was absorbing green, yellow, and red. It's a subtractive way of making color. AKA, you basically removing part of the visible spectrum by absorbing it in the chemical structure. Now, you can get colors through a structural way, which is not a chemical way, in which, in this case, is an additive process. So instead of absorbing certain wavelengths of light, you can just decide that you can have a periodic structure, which is called a photonic crystal, and that is going to reflect specifically the wavelengths of light you want to see. So now you want to make something blue. Instead of absorbing red, green, yellow, etc., you're going to make a periodic structure, so something that is very regular, with the periodicity corresponding to about the wavelengths of blue light, so 450 nanometer, and it will reflect just blue. That's what structural color is about. You see it in natural system. You see it on butterfly wings that have iridescent colors, in some plants that are also iridescent. That's something that biopolymers do in nature all the time. And what we're trying to do is do this in those natural fibers that we're making so we can have the color at the moment you form the fiber. You don't have to form the fiber and then dye it. You control the nanoscale arrangement of those molecules in those filaments, etc., so that you can get reflectivity of the specific color you're trying to see.
So that work is happening right now in your lab.
Yeah, so we've made films. We built a fiber spinner where we're extruding some of those gels that are colored and trying to see the color reforming. And then we're trying to modify the chemical structure of the natural polymer so it can be both stretchy and colorful. And that's actually really hard.
If you could make, let's say, an absurd color effect happen in this fabric, what would you choose? Like a mood ring shirt or a shirt that changes when someone's lying? So it would be like a tell. Is that in the near future? Because that would be super helpful for me.
I mean, that'd be helpful for you, but in reality, Seth, do you want your jacket to look iridescent when you are on the L? No, you don't.
Good point. Yeah.
There's also that to manage, right? A lot of those structural colors are iridescent, and the colors we are used to are not iridescent. What we're also doing is you can also change the nanoscale arrangement so that the color, instead of being iridescent, like the wings of a butterfly, can still be matte. So it will look more like a chemical color. Yeah, you can have a mood ring shirt if you want, Seth, but in general, you're not going to show up at work with your mood shirt.
It would let people know, like, oh, he's having a day. Let's not bother him yet.
If things are actually designed with this whole idea of the life cycle in mind, with the things that we are so used to just 7 wears done, would it be a different experience as the consumer?
I think you have 2 ways of doing this when you approach the fundamental science. You can decide what people want to do with their clothes is basically set in stone. And I have to design something that's going to withstand 7 wears, be done, and not be a toll on the environment. Or you can say there needs to be changes in the consumer approach of garments, and they're going to have to wear it more than 7 times. Here is the thing. One of those 2 scenarios I have control over. The other one I have a lot less control over.
Can't force people to hold on to a sweater for 10 years, right?
And some of us are going to do it, and some of us are not. It's funny because when I tell people that statistics, which is in the United States, people wear a garment on average 7 times before they throw it away. And I'm telling academics this. Academics look at me and say, I've had the same suit for 15 years. And I was like, I'm sorry to tell you, you are an academic. You are also not the most representative average person. The part that is within our control is to sensitize the public what happens when they throw a polyester piece of leggings that they wore 4 times out in the trash. And that's where I have a role to play to basically explain to them, this is what happened, this is how polymer breaks down. But that's about the extent of the contribution I can have to that second scenario. So the idealistic scenario for me is we change the polymers, but we make it all the way that the consumer almost doesn't see a difference. So we use biopolymers that are abundant, so they're cheap. A lot of the biopolymer we use are actually developed at thickening agent for cosmetics or for food. So they're already produced at very large scale for very large consumer applications. So the cost is already down. Then you're like, okay, I'm going to have to modify them. So I'm going to have to do chemistry on them. How do I think about my chemical process so it's not horrible for the environment itself? There's no point for me tackling the dyeing process if my synthesis process is going to be absolutely as horrible and use as much water. And there's a lot of fundamental questions on that side of things. You have to develop new chemistry. You have to think about this. But with this idea of how does I make it as painless for the consumer to actually look at it? So I don't think I have an answer to your question in and of itself, but I think there's things we can control as scientists and there's things we can only help sensitize about.
What about other industries outside of apparel, like aerospace, medical infrastructure? Certainly there's a need there as well for improvement.
There is. It's the same with the history of polymer chemistry. It started with textiles, but also synthetic polymers then got used in aerospace, in medicine, and all that stuff. And things we'll discover along the way that are not necessarily just for textiles. And maybe we're going to find this biopolymer derivative that's not very good to make fibers, but is actually very good to make cutlery or very good to make disposable gloves for medical people. There's a thing about polymer in general. Once you understand how the necklaces pack with each other, how they slide with each other, and how they potentially form those higher multiple length scale of order, you can basically control it the way you want.
What does happen to those leggings when you throw them away? I mean, you donate it and it doesn't get bought at the thrift store. What happens to those fabrics?
I'm obviously not an expert, but in general, it goes in the landfill. And then, as you were pointing out, it doesn't break down. So most of the time, you're going to have little fibers of it that are going to just fall off. If you look at your sweater, each fiber is not a single monolithic fiber. It's a bunch of little fibers that are twisted together, and that's called a yarn. When you put it in your washing machine, some of those yarn, tiny filament, break down and they go out in the waterways and they just stay there because they don't break down. And there's a lot of degrees on how widespread and somewhat invasive the waste is. And it's not just you throwing away your garment, it's you washing your garment on an everyday basis. It goes in the washing machine, it's being tumbled, it's shedding a bunch of fibers that goes in the waterways, and that's just there. It's the garment staying in the landfill somewhere. It's you incinerate it and it creates CO2 emission because you burned it. It's not great. Keep your garments for as long as you can.
And buy natural fibers?
So that's the thing also, it's common sense. In any case, if you're going to buy it and you know it's going to be perhaps harmful for the environment, perhaps wear it for longer. You know, trends come back.
Oh yeah, 90s are back. I'm going to be cool again, I swear. All those clothes that my mom never got rid of. I'm going to wear them again and everyone's going to like me. It's going to be great.
That's the thing I was saying that's not really in our control, right? It's this idea that we went from having 2 seasons of clothing from having new garments every week. And that's a habit change. That's something I don't control as a scientist. But what I can control is if it's going to be a new garment every week, can I design it in a way that it actually breaks down? And with nanoscience, so you don't have to dye it.
So you're drawing inspiration from biological polymers like cellulose, which can self-organize into ordered structures. What can natural materials teach us about designing synthetic ones that are both functional and recyclable?
It's basically this idea that how can such a messy system like nature make polymers that can order so well from a zero point 0.1 nanometer scale up to micron scale? And here we are, chemists, thinking we can control every bead of that necklace. And for some reason, we can't get things to self-assemble nearly as well as nature does it. Or we can make it, but it's so effort intensive that you're looking at a plant and you're like, how did you do it? You did nothing. You just grew. And I think that's really what we can learn from that. So cellulose is a polysaccharide, poly and saccharide meaning sugar molecules. So the bead in your necklace are sugars, glucose, fructose, etc. If you were in a lab and trying to take glucose and polymerize glucose, it's really difficult. It's so hard. And plants and organisms and fungi do it all the time. We're here in the lab being like, I put 10 beads on my necklace. It took me a week. It was so difficult. And here they are. You extract cellulose from plant and you get number of repeat units that are like 100, 120. And then they have all those regular arrangement across 3, 4, 5 orders of magnitudes of length scale. I think this is what we have to learn is quite frankly is this aspect, like there's a complexity in nature that we have a hard time reproducing despite being fully in control of the molecular chemistry of it and how they're attached with each other.
So like if you're out for a hike, do you look around nature and are you jealous of it or do you get inspired?
My research in photonics was in bioinspired optics, right? So I would go to the botanical garden and try and find all the iridescent flowers and be like, can I put this in the microscope? Is this structural color? Because this one is iridescent. I'm going to grab this one. Like, I had a friend in my previous research group. We would go to botanical garden trying to find the flowers that look iridescent.
And just wait for one of the petals to fall off and be like, oh, it fell. It's mine. I can use that now.
Yes, exactly. I can't pick it, but there's a name. So I can look up the name on Google. Has someone put it in a microscope? Can I put it in the microscope?
So looking ahead, when could some of these materials make it out of the lab and into large scale manufacturing? And what are the biggest hurdles that you're seeing right now?
Optimistically, my hope is in a 5 to 10 years range. We can make enough of those structurally colored fibers that we can at least weave them into a little patch, like 4 inch by 4 inch patch. What we try to do is from the get go, we try and design the process on the lab bench that's just a miniaturized version of an industrial process. And we do it at a small scale. Instead of making 50 kilometers, we make, let's say, a couple meters. And I think I would love to be able to get there 5 to 10 years, because then I think the convincing side of telling others that have large spinning facilities that make 10, 15, 20, hundreds of kilometers of fibers is a much easier sell. And we take this actually really at heart. For instance, we demonstrated that you could coat elastane fibers with chitosan, which is another of those natural polymers that's extracted from crab shells and fungi. And we wanted to demonstrate that you could do it in a roll-to-roll process. What a roll-to-roll process is, you have a spool of fiber on one end, and it goes through a bunch of little rolls, and you can pass it through a bunch of different baths. And then you collect it on a roll that is the finished fibers. So the starting fibers is just elastane. The finished fiber is coated with that biopolymers that helps recycle it. We basically made this little benchtop roll-to-roll where instead of using a spool of elastane this big, we basically wound it onto a sewing machine bobbin. And the starting roll is a sewing machine bobbin. It's motorized. And the collecting roll is an empty sewing machine bobbin. And we said, look, we can do it roll-to-roll. It's a smaller version, the version that's on a sewing machine bobbin, but it's still the same process that you could do at large scale in your large manufacturing plant.
Your work sits at material science and chemistry, mechanics, textiles. When you're building a project team, because this is a very interdisciplinary field, what do you look for from day one when you're trying to assemble your team?
That's an excellent question. It's so funny because my degree is technically in material science and engineering. I only ever did research in mechanical engineering and manufacturing, and we do polymer chemistry too. My team is actually some mechanical engineers who build the manufacturing setups and try and understand the manufacturing process. I also have chemists who are very good synthetic chemists who understand how to modify those molecular structure. And then I also have material scientists and engineer, or as material scientists, our bread and butter is what we call phase diagrams, which tells you what is the state of matter at different composition. And they basically try and understand what are the energetic driving force for things to form more filaments, to form those hierarchical orders. And can I build processing maps that tell me I should be using the solvent, or I should be evaporating the solvent this quickly? How does that change the nanostructure? How does that change the color I see? I think that's the beauty of Northwestern too, is I can have all those people. I have all those students and postdocs and amazing people who speak different language and end up in the lab working together.
Cécile, thank you so much for joining us. It was amazing, and we hope to have you on again soon.
Thank you. Thank you so much, guys.
Thanks so much for listening. This podcast is brought to you by the International Institute for Nanotechnology at Northwestern University. Be sure to follow this show on Apple Podcasts or wherever you listen to podcasts, and be sure to give us a 5-star review.
For more information about IIN, go to our website, iinano.org/podcast.